Welcome to the Electrical and Electronic Engineering Lecture Series. Your anchor person is Professor Michael C. Ndinechi. Our topic today is Model 038, Telecommunication Standards and Regulations. Please join me in the Engineering Lecture Series by subscribing to my YouTube channel at https://youtube.com/@ndinechi-michael-c. Please like, share, and drop your comments in the comment section or reach out to me using my email addresses. Listen to my other related lectures to the topic we are going to treat today at http YouTube dash the three links given all related to the lecture we are going to have today. Also, I would like to introduce this website to you, Ebony Educational Consult website. For free online lectures, you can visit the website by clicking on www.ebonyeducationalconsult.com. There, you will get many of the free engineering lectures. Like our topic stated, we are going to look at telecommunication standards and regulations. So, why standards? Standards play a major role in telecommunications by 1. Allowing products from diverse suppliers to be interconnected. 2. Facilitating innovation by creating large markets for common products. For instance, small manufacturers, if there are no standards, they may be limited to only people that are willing to risk connecting to their system. Larger organizations will mask smaller ones out and monopoly will set in. So, standards helps younger ones to innovate and come up with a product that can also fit into the market. The standards making process is one of the cooperations at many levels, both nationally and internationally, and includes cooperation between 1. Industrial concerns within a country. For instance, in Nigeria, if we use the GSM market, for instance, we know that there are 4 companies that provide GSM services. These 4 companies must work in synergy for them to move on. So it is the standards set up by telecommunication stakeholders that help them or assist them to work together. Else, one may think that it has a larger market and try to squeeze the other one out of the market space. So industrial concerns within the country must, come together, work in cooperation with each other to achieve result. Then these industrial concerns and their governments must work together, because in terms of disagreement, the government must come in. For instance, the government has to set, the billing standard, probably cost per minute of a call, so that it becomes uniform amongst the companies. So there will be no unfair competition. Again, it has to go between national governments at the international level. When we say national government at international level, so that government of a particular country will be able to liaise with another country, and also for people roaming, moving from one country to another, there must be a network in that country that will also receive their calls, and at the end of the day, there must be some kind of trade-off, balancing and counterbalancing, so that you see that these standards help national governments to operate at the international level with other. So the primary purpose of this standard in telecommunications is to specify how different devices communicate in a diverse environment and with different networks, more especially mobile devices. This includes specifications of the following. 1. The signals to be transmitted and received by the mobile phone. 2. The format of this signal. Remember, in mobile systems, we have different formats. We have the GSM, we have the CDMA, we have other models. So how do these signals emanating from different models, different designs, interact? It is these standards that we specify them. And also, of course, as we go on, we see that the frequency of operation has to also be monitored. So, 2, the format of these signals has to be stated standard. Again, the interaction of network nodes, how the network nodes, that is the devices involved in this communication, how they interact with one another. That is how the product from this company interacts with the product of that company, how you get a SIM card, irrespective of the device you put it in, it will understand the SIM card. That is the interaction between different nodes. The basic network services which should be available to mobile users, for instance, they're going to be receiving data, video, or only voice calls. So all these things are things that are specified by the standards. And finally, the basic network structure. For instance, in the GSM system, you have, cells. Other communication systems, we have other network structures that allow them to operate. However, whichever network structure the operator is operating, it must be able to connect with another vendor that is using a different network structure. This is how standards become very important in telecommunications, because they have to specify. In any country, there are agencies that are in charge of handling these standards. So, as an assignment 1, I want you to name in the comment section, two agencies in your country that are responsible for setting telecommunication standards. If you do that in the comment section, I'll be able to reach out to you and correct you if you are not correct, and of course tick you good if you got it right. Then come the international regulations. We have seen how standards, specify things, but there must be regulations to guide how these operators enforce the standards. So we say for a complete communication network, it is important that individual systems within a country need not only be interconnected, the whole national system must be connected to the international system. The problem with such an interconnection is that there are different types of communication systems used in different countries, which have been built to different specifications and standards. Therefore, there is need to specify certain common standards that will be applicable to facilitate international communications through networks that are millions of kilometers apart. The body charged to do this is the International Telecommunication Union, otherwise known as the ITU, which is based in Geneva and was set up by the United Nations and charged with the responsibility of preparing recommendations for proper working of long international circuits. These long international circuits are at times referred to as hypothetical reference circuits, HRC, specify standards where one transmission system is crossing the other one. At what angle will it be to minimize interference, and so on and so forth. So if you subscribe to my channel, time will come when I will be treating microwave design and rolling out. We will see how these long international circuits are being designed and deployed to minimize interference with other systems operating in the microwave range. So this ITU, International Telecommunication Union, performs these functions we mentioned via its three arms. One is called the ITU-T, ITU Technical, ITU-R, that is ITU Radio, and ITU-D, which is International Telecommunication Union Development. This ITU was founded in Paris in 1865 as the International Telegraph Union. Well, as at that time, what was in vogue was the telegraph, communication. So it was founded that time as International Telegraph Union. But it took its present name of ITU in 1932, and in 1947 it became a specialized agency of the United Nations. Although its first area of expertise was the telegraph, the work of ITU now covers the whole of ICT sector, from digital broadcasting to the internet, and from mobile technologies to high definition television and 3D television. So you see that it has moved from the original idea of governing telegraph But as technology develops, it has to move to cover new, discoveries, new things in telecommunication, which covers all form of ICT and information superhighway, the internet, and of course, digital broadcasting. So this ITU is an organization of public-private partnership since its inception. ITU currently has a membership of 194 countries and over 1,000 private sector entities. Now, the question is, United Nations, but it's having public-private partnership. The essence is that the development of new technologies lies with the private enterprise. But the private enterprises, if you leave them alone, there will be monopoly. So it becomes an organization between the countries and the countries that made up United Nations and public-private partnership, so that the companies will know the specifications when they are developing their products. They will be, forced to, develop according to standards and regulations, or else when they develop in isolation, then their product will not be able to, enjoy the global market. So that is why it is an organization of public-private partnership. The work of the union was subdivided into 3 bureaus, one each for radio communications, that is ITUR, the telecommunication standard, which is the ITUT, and the telecommunications development, which is the ITUD. Each of these sectors will have an advisory group drawn from member states as well as the private sector to advise the directorate of the bureau on the work of his or her sector. At this point, I will also want you to nose around to see for your country which advisory group they are part of. Every country, which is member state of the UN, we participate, but not all countries have what it takes to participate in all the groups. So they belong to one or two or three of the groups. Now, there are regular cycle of conferences which was established to help the union to rapidly respond to new technological advances. And this conference is known as the WAC, or World Administrative Radio Conference. At this conference, people go to, present their new discoveries. That could be in equipment, in management of the frequency spectrum. Frequency spectrum, even though we say it's free, but then it is highly managed, because without coordinated management of the spectrum, there will be chaos in the sky. So the union, at this conference called WAC, we converge all organizations, countries, private people to come and present their new areas of discovery. For instance, if somebody is already working on 7G, it is in this conference that we come to sell his idea of 7G. so that if he gets approval, he can now start developing equipment and products in the 7G. So with that, others will see, okay, the next trend is 7G. So they will move into that and also start working so that there will be no room for monopoly. That is the essence of this World Administrative Radio Conference known as. So, what are the functions of these three arms of the ITU? The first one here is the ITUR, say the ITU radio. This ITUR is formally called the CCIR. CCIR means International Radio Consultative Committee, and it is responsible for the preparation and recommendations relating to radio and microwave systems. ITUR has a mission or missions which include to ensure interference-free operations of radio communication systems by implementing the radio regulations and regional agreements. 2, to update radio instruments in an efficient and timely manner through the processes of world and regional communication conferences. Remember, the World Administrative Congress conference is where everybody comes, but there are regions. ITU is divided also into regions because due to environmental and weather conditions, the frequency that may be very good for us in radio broadcasting may not be very good for some other countries in non-temperate regions. So you see, each region we have to come up with what is good for them, more especially in the radio communications, which is mainly on microwave and long distance international circuits. So they have to do that at regional level, then take it to the global level, which is the WAC conference, to get approvals. That is why you can see that the frequency of operation of certain telecom system in Africa does not correspond to the same operation in North America or in Asia because of the environmental weather conditions. So their mission also include to establish recommendations intended to assure the necessary performance and quality in operating radio communication systems. Again, includes to seek ways and means to ensure the rational, equitable, efficient, and economical use of the radio frequency spectrum and satellite orbit resources. Now, when we treat satellite communications, you see that the satellites are placed in the geosynchronous orbit. So this geosynchronous orbit is a particular radius from the Earth, and if care is not taken, some highly developed countries will occupy all the orbits, and developing countries that may be developing their own satellites in the next 5, 10, 20 years will not have the orbit where to put their resources. So these are part of the regulations that are under the ITUR. And finally, their responsibility include to promote flexibility for future expansion, because definitely telecommunication is not going to remain stagnant. So as it improves on daily basis, people will have to project into the future to see what is the possible thing that the future holds. Then the next arm is the ITUT. This ITUT, formerly called the CCITT, that is International Telegraph and Telephone Consultative Committee, is responsible for setting standards of operation and interoperability for telecommunication networks. You can see that. So they are responsible for the technical operations of telecommunication network. Their former name was when, telegraphy and telephony was the main, thing about telecommunications. So as the drifts moved from just telegraphy and telephony, then the name changed to ITU Technical. The ITUT mission is to ensure the efficient and timely production of standards covering all fields of telecommunication and information technology on a worldwide basis. That is why we have, standards like, the IEEE 802 dot, which is, for Wi-Fi, and different versions of IEEE standards. So, defining tariff and accounting principles for international telecommunication services is also one of the major missions of the ITUT. Then, the ITUD, the telecommunication development sector, which is the ITUD, fosters international cooperation and solidarity in the delivery of technical assistance and in the creation, development, and improvement of telecommunication and ICT equipment and networks. Their key objectives is one, to foster international cooperation on telecommunication and ICT development issues. Two, to foster an enabling environment for ICT development and the development of telecommunications and ICT networks. Again, their objective includes to enhance confidence and security in the use of telecommunication and ICTs. One imagines what will happen if there is no standard for maintaining security. Then you can, imagine what will have happened with all the, security in place. There is still, means of hacking into the system. So see that it is a key work that every telecommunication system maintains some level of confidentiality and security. Now, one of their objectives is to build human and institutional capacity. They must, train people, the digital natives, what we call the young people now, the digital natives. So they have to, be trained. So that human capacity is very necessary to sustain the future. And again, to provide data and statistics, promote digital inclusion, and provide concentrated assistance to countries in special need. I think this is, very clear. Promote digital inclusions. Of course, you'll be hearing of digital divide between developed and developing nations. between genders and between some countries that may be in special need. It is the work of the ITOD to help to get these statistics so that the UN will know the extent to help a country so that they can meet up with the basic standard. So the next thing we will look at is this frequency spectrum. Remember, you cannot talk about communications without mentioning frequency and frequency spectrum. So it is important that at this point in time, as students of telecommunication engineering, we must know everything about spectrum and frequency spectrum. So the radio waves are classified by their frequency. The other way of measuring frequency is the wavelength. So as the frequency increases, the wavelength decreases. And formula for wavelength, which is always represented as lambda, is equal to c over f, where c is the speed of light giving us 3 times 10 raised to power 8, and frequency is equal to is given in hertz. So at this point, it is good for us to note that very low frequencies can travel tremendous distances but carry little information along with it. And that is why if you have your radio known as the world receiver, you see that from your country you can receive distant stations but at the low frequency band. So as we go on in this lecture, we will see the frequency ranges that are low frequencies and the ones that are high and the ones that are ultra high and extreme high frequencies. So let's follow us in this lecture to get all this information and get abreast of the frequency and why they are used for a particular application. So the table below shows the class, name, mode of propagation, and special features of typical radio spectrum. Remember, you can say radio spectrum, frequency spectrum, the mean the same thing. So this table, if you look at the left side, you see the frequencies, the name of the frequencies, the mode of propagation, and the special features which each of these frequencies offer to telecommunication applications. So we start by having the 0.3 kilohertz to 3 kilohertz. So that this range of frequency is known as the voice frequency. And there's no special mode of transmission, and the special features about it is used for speech. So this, my voice you're hearing, is having frequency between 0.3 kilohertz to 3 kilohertz. So depending on the pitch of your voice, your frequency may be higher. So from 3 kilohertz to 30 kilohertz is called the very low frequency, VLF. And its mode of propagation is through the 8th ionosphere and waveguide. So if you subscribe to my channel, the time I will treat waveguides, you will know exactly how it operates. But the surface of the earth is stratified. You have the ionosphere, the troposphere, and the sky, and the space. So depending on your frequency of operation, then your propagation will take place either in the ionosphere, in the troposphere, in the sky, or in the space. But this very low frequency, operations or signals are through guide them, or through the 8th ionosphere, serving as waveguide. How does it serve as waveguide? If you propagate your signal, it gets to the interface between the ionosphere and the troposphere. It is reflected back, it hits the earth, it's reflected up, it continues like that. So this 8th ionosphere serves as a waveguide that carries the wave almost round the surface of the earth. That is why you can stay where you are and listen to Voice of America, the BBC African service, because it's a low frequency signal, and the 8th ionosphere serves as waveguide that allows it to propagate almost round the surface of the earth. So the special features associated with it is long distance worldwide communication, low fading. We've talked about fading in one of the lectures. It's used for military and navigational applications. It makes use of very large antennas and in some cases not very efficient. Now you can see, because it is almost worldwide, military people who are very far away from their country can easily communicate to their country, and a large merchant ship who is in far away sea from its country of origin can equally communicate to the base. See why it is used for mainly military and navigational applications, and fading is very minimal. So the next band or the next frequency range is 30 kilohertz to 300 kilohertz. It's called the low frequency. Remember, the first one is very low, this one is low frequency. And we say that in this one, propagation is by ground wave with small amount of sky wave. Also, in future, we'll be looking at radio wave propagations, in which case we will treat this ground wave and sky wave very well. So the special features with that is LW band. If you have world receiver, that small radio called world receiver, you will see that there is LW band. So this transmission in this range gives a bit stable transmission. Fading is still little due to sky wave, which is up to 1,500 kilometers. So in this frequency, you can transmit up to 1,500 kilometers. Your signal can travel that length before degrading to a level that cannot be received by the receiver. So they also make use of large antennas, but because it is going by part sky wave, you see that the atmospheric noise, which we have treated in our previous lecture, affects the transmission here. You say that it has high atmospheric noise. When we talk of atmospheric noise, we are talking of the cosmic noise, which comes from the extraterrestrial body, the sun, and the stars. So The next level is 300 kilohertz to 3 megahertz. And say that it is known as the medium frequency or medium wave frequency. Some people call medium frequency, some call medium wave. If you look at your radio also, you see the band that is labeled medium wave. So that frequency is propagated through the ground wave for short distances and sky wave for long distances. So the medium wave band is used for broadcasting. It has more fading but has less atmospheric noise affecting it. So it has more noise than the high frequency. That is the next higher frequency range, and it is reliable up to a few hundred kilometers and is mainly used for commercial radios. That is why when you buy your radio, you see the medium wave band, and some radio stations are operated in that range. So we continue from 3 megahertz to 30 megahertz. It's called the high frequency, and the propagation is by sky wave. So here has special features in the sense that fading is often severe. Noise is less important than fading here. Noise may not really affect the signals here, but the signals will fade more rapidly. We have defined what fading is as loss of signal as seen by the receiver. So now this frequency used in mobile land communications and from ship to shore. Then we have the 30 megahertz to 300 megahertz frequency range, which is known as the very high frequency band. This very high frequency band is propagated by space wave. So when you operate at the space wave, it means that your communication must be line of sight communications. Well, future we'll be looking at line of sight when we deal with microwave designs and rolling out of microwave systems. So the VHF length is, which is common when you are now having your repeaters. You use your VHF to move signal from one repeater to the other, more especially when your communication is a long haul communication. So here again, fading is a problem due to the structure of the atmosphere. Atmospheric noise is severe, low antenna structure, and used for VHF television. In those days, where you have your CRT TVs, you see that you have the knob called the UHF and the knob called the VHF. The VHF helps you receive distant television stations, distant, not necessarily outside your country, but the UHF helps you to receive very local one, probably only TV stations that is certain radius within where your TV set is. So I say that for the VHF, it makes use of low antenna structure. That is why you can put your Yagi antenna on top of your roof and receive your VHF channels. So further up, you have the 300 megahertz to 3 gigahertz, which is known as the UHF, ultra high frequency band. So here, propagation is through space wave or scatter wave. Now, when you beam your signal into the space, there is the refractive index of the space, water molecules, and different layers. So when this signal meets different points of different refractive index, then the signal starts to scatter. Some may come back to the earth, some will escape further into the space, never to return back. So it may go and return to a far distant place. So you see that if you plan it very well, those scattering will enable you to drop your signal different places within the Earth's surface. So we call it scatter signal, because at that point you scatter them. Well, there is computations and calculations that help you to know where the signal lands, but it is not for us here. So at this UHF band, there is line of sight short distance communications. Fading is a big problem. So when you use that, you see that you must have your repeaters within about 50 kilometers, or else your signal will fade completely, that it cannot be recovered. So there is also presence of galaxy noise. We know all what is galaxy. If we don't, we refer you back to your geography class to know what is galaxy. And of course, our own galaxy is called the Milky Way. So it makes use of small antennas. That is why your UHF TV can just have a dipole antenna at the back of the TV, and you use it to receive your signal. So this antenna has very high gain and directivity. When you are using your UHF TV, you see that you keep, if you want to receive a station, you try to turn your antenna to in the direction of that TV station. That is exactly what you do, because the signals here possesses high level of directivity. So from 3 gigahertz to 30 gigahertz, you call it the super high frequency, and the propagation is entirely by space wave, and have it as line of sight satellite links, microwave radio relays, high atmospheric absorption is here, radar for surveillance and weather operates in this frequency range. Also, at the 30 gigahertz to 300 gigahertz, it's called the extreme high frequency band. And propagation is again by space wave. So it's used for radar and landing systems. Landing systems is for aircrafts. Then it's also for line of sight satellite links, has very small antennas with very high gain. Of course, it has high atmospheric absorption. When we talk of this high atmospheric absorptions, it means that water vapor has significant effect in transmissions at this level. Then above the 300 gigahertz, we call it infrared, takes place there, the laser beam, the optical fiber communications all operate at these frequencies above. So we look at another assignment. Say, now find the upper and lower wavelength of each of the frequency ranges in the frequency table above. So for instance, we have the voice signal from 0.3 kilohertz to 3 kilohertz. So using the formula given, find the wavelength for the lower part and the wavelength for the upper part. Then when you do that, you will see that the wavelength of voice signal is between this and that. So I want you to do the same for all the frequency ranges we have mentioned there, the voice, the low, very low frequency, the low frequency, the high frequency, the UHF, the VHF, and so on, so that on your own you will be able to see. If you see a wavelength, tell you that this telecommunication operates at this wavelength, you'll be able to know the band that is being referred to. So do that and let me see them in the comments section. Note, there are names that are used to represent some frequency ranges, more especially at the gigahertz level. So when something is operating, any telecommunication service is operating in the 1 to 2 gigahertz, it is said to be operated in the L band. So it is not always for you to start remembering this, but you can remember the bands. So 2 to 4 gigahertz is called the S band, 4 to 8 is called the C band, 8 to 12 is called the X band, 12 to 18 is called the KO band, 18 to 27 is called the K band, 27 to 40 is called the KA band, and 40 to 300 gigahertz is called the millimeter band. Now, you can notice that at times when you're watching your satellite TV and rain starts, you see they either tell you that they are searching for signal in the C band or in the KU band or in the K band. So you see that because the operation there is by space propagation, and from what we have seen, we say that there in the space propagation, atmospheric disturbance is much. So you see that rain really affects signal at this level. So they try to see where the effect of rain is a little bit less. And in most cases, when they can't find it, you lose the signal. The system will warn you that due to bad weather or faulty connection, you are not receiving. But immediately the rain subsides, you start receiving your signal again. So you can see for any telecommunication operation you're having, there is a frequency band that is most suitable for you. In some cases, it will be a trade-off. And that is what the International Telecommunication Union begins to determine in your place what is the best frequency spectrum to perform a particular task. So now, there is one important thing about these radio waves. It has so much difficulties. So when you are planning your telecommunication services, you have to take care of some of these difficulties, which we will quickly run through. So amongst the major factors associated with radio telecommunications are: 1, path loss. Radio signals lose power at a rate that increases with the square of the distance from the transmitter. at a rate that increases with the square of the distance from the transmitter. It is not as simple as this when you talk of path loss, but we are just first bringing it to your knowledge. As we go on, we start developing even formulas and models for path loss. Then we have the second one, which we call the path obstacle. Radio path loss increases when the signal passes through materials like metals, water, and concrete. In fact, when your transmission is going across a large body of water, it becomes a very difficult, because at grazing incidents, something happens, your signal is attenuated, and we know that reflections must take place when you transmit your signal. It is not just, even if it is line of sight, it is not just a straight line. It has what you call the Fresnel zone around it, that if you have any object within the first Fresnel zone, you now have your signal to be degraded and attenuated. But like I said, those details are not for us now. When we go up in our lectures in telecommunications, we will come across all these items. So, higher frequency signals experience greater loss than lower frequency signals when faced with these obstacles. We have what we call the multipath fading. Multipath fading occurs when there is more than one transmission path from the transmitter to the receiver. This may be due to buildings or mountains either close to or far from the receiving device. That is, if your signal output from the transmitter is strong enough, one set of signal may get to the receiver direct, while the other may be reflected from a building, distant from the receiver. If the receiver receives this reflected signal from the building and it is still strong enough, then it will interfere with the one received direct. So it will either cause constructive or destructive interference. In most cases, destructive interference. And when we do our microwave line of sight design, you will see how we mask off these reflected signals to avoid this type of fading at the receiving end. So this multipath fading may be due to buildings, mountains, either close, we have said that. So we have what we call the relay fading. This relay fading occurs when a signal takes more than one path between the transmitter to the receiver. In this case, the signal is not received on a line of sight path directly from the transmitter antenna. Rather, it is reflected off buildings and is received from several different indirect paths. I want us to pause here and look at it with the first one, which we say multipath fading. In the multipath fading, one signal moves direct from the transmitter to the receiver, while another one is reflected from, let's say, a building close or far away from the receiver. But when we talk of the relay fading, we are talking of there is no one that comes direct from the antenna. All that is received by the receiver are reflected ones. Some reflected very close to the receiver, some very far away from the receiver, So when all these reflected signals converge at the antenna, or the receiving antenna, they cause what is called the relay fading. So it is important for you to note the difference when we just talk of multipath fading and when we talk of relay fading. Even though relay fading can be seen as being close to multipath fading, but there is a slight difference, and that is what we are stating in this second line, where we say that in this case the signal is not received on a line of sight path directly from the antenna. Rather, it is reflected off buildings and is received from several different indirect paths. Please note that. Relay fading occurs when the obstacles causing it is close to the receiving. So now we have another one which is called the time dispersion. Time dispersion is another problem relating to multiple paths to the receiver of either the transmitter or the receiver. In contrast to relay fading, here the reflected signal comes from an object far away from the receiver antenna. Time dispersion causes what is known as the inter-symbol interference, where consecutive symbol bits interfere with each other, making it difficult for the receiver to determine which symbol is the correct one. We shall see that shortly. The figure below illustrates that sequence of 1, 0 from the transmitter. So let's look at this sketch here. You see your antenna and you see your receiver, which in this case is your mobile device. So this antenna in fig 1, or the one there, transmitted 1 bit. So 1 bit gets to the antenna, to the mobile device, while 1 bit gets to the mounted there. So after it transmitted 0 bit, the same 0 bit followed the 1 bit to the receiving device. The same 0 bit followed the 1 bit to the mounting. Then in the third one, the right one, you now see the first 1 bit is reflected by the mounting, and it is that reflected 1 bit is getting to the receiver or the receiving device. At the same time, the 0 bit, which is the second one transmitted by the transmitter, is getting to the receiver. So the receiver at this point sees 2 bits. 1 is 0, 1 is 1. The receiver will be confused on which one that is the correct one. So this confusion is what is called the inter-symbol interference. So it is mainly predominant when you have digital transmission. It also occurs in the analog. So if we continue quickly, you see that foliage, when water in leaves, if you have vegetation and your transmission, we have to go through that place. Water in leaves absorb radio signals, thereby leading to the attenuation of signals. Then weather effects, mentioned that rain and snow, for where you have snow, also reduce signal strength. So different radio frequencies are affected to different degrees. So when you are doing your operation, you have to consider all this to know the frequency range where you are going to be operating. Higher frequencies are more susceptible to adverse weather conditions than low frequencies. Then we have what we call the shadowing. Shadowing occurs when there are physical obstacles, including tall buildings and hills between the transmitter and the receiver. The obstacle creates a shadowing effect which can decrease the received signal strength. Remember that time during our class in geography, tell you that you have what is called orographic ray. When the cloud carrying water vapor comes to where there is highland, and you see it's reflected up and now get condensed and fall back as rain. So it doesn't allow the cloud to cross over to the other side. You call the other side the leeway of that mountain. So in telecommunication, similar thing happens, that when a signal meets an obstacle, tall buildings or hills, then it finds it difficult to reach the receiver that is behind that. That is why when you see transmission repeaters, you see them some on top of the buildings and on top of highlands, so that those highlands will not cause shadowing. So now its effect, that is the effect of shadowing, is felt more in mobile devices, wireless mobile telecommunications, which leads to signal strength fluctuations. So at this point, we look at other assignments. And we say for this assignment, and for each of these telecommunication transmission difficulties we have started, we want you to profile a solution. For my students, this must be submitted. The transmission difficulties, they all have solutions to them, so that if you're doing your transmission and you find out that what is your problem is shadowing, how do you take care of it? And you see that what you are experiencing is path loss, how do you take care of it? So we want you to look at those problems and profile solutions to them, because there are solutions. Then the next assignment is neither here nor there. We know that one school of thought is talking about the effect of radiation of all these radio signals on human beings, and some people are saying it doesn't have any issue on human beings. So at this point, we ask you, as the telecommunication student, what is your take on health issues associated with radiation of electromagnetic waves on human beings? Give me your answer in the comment section. So quickly and finally, we look at this radio frequency spectrum utilization. So though radio frequency spectrum is ubiquitous, their use for a particular operation is limited by the radio window for such operation. When we talk of radio window, we look at the frequencies before that, why they are not suitable, and the frequencies after that, why are they not stable. For instance, if you have your radio, you see that your FM radio operates between 88 and 108 megahertz. Your FM radio, 88 to 108 megahertz. So why can't you operate below 88, and why can't you operate below 108? So you see that there is a window that allows FM radio to operate between 88 and 108 megahertz. So for every telecommunication operations, for satellite applications, for radio, for ship to shore, for navigation, they all have radio windows. So say that even though it is ubiquitous everywhere, their use are limited by the radio window for their operations. Their use must be shared amongst thousands of different users. Each user will require a number of separate channels to maximize his channel. For instance, here we have 4 GSM companies, and each one is assigned limited number of channels. As we go on, we will see how they manage these channels to accommodate the number of subscribers they have. So also, this radio frequency utilization has 4 basic techniques for maximizing them for their users. The first one is the space division multiplexing. So as radio signals lose power over distance, the same channels can be reused so long as the transmitter are far apart as to prevent interference. This phenomenon is known as co-channel interference, which is the basic concept of cellular networks. Then we have the B, which is the frequency division multiplexing. So this is a multiplexing technique in which the available transmission frequency spectrum is divided into bands that are used for separate channels. Here, different parts of the radio spectrum are assigned to different users. Of course, we have the time division multiple access, which is known as TDMA. In the TDMA, a single radio channel can further be shared by allowing different users to send bursts of transmission on that same frequency channel. And here, different users take turn to transmit on the same shared channel. And of course, we have the last one, which is the spread spectrum. There are also branches of this. So as we go on, we will see those branches of spread spectrum. In a spread spectrum system, a number of different users send at the same time in a much wider frequency band. The receiver disentangles the various frequencies, so all the other frequencies seem to be background noise to it. If we are to illustrate this in the class, we will bring maybe out 4 people coming into the class through the door, and each of the 4 people will be wearing different color, maybe red, yellow, black, green. So people inside with color blind, if they are coming in, even though 4 of them are coming in at the same time, somebody that is blind to, color blind can only see only the black person. So that is the technique employed here, that so many signals are transmitted over the channel at the same time, each receiver sees only the one that he wants to see, that he has been designed to see. Every other one will seem to it like background noise, and he will not see that. So that is the technique employed in spread spectrum. So the main advantage of the spread spectrum transmission is that if there is interference or fading in one part of the frequency band, the receiver may still be able to receive enough of the signal to reconstruct it. So for more information on this, last part, which we call multiplexing, so see my lecture on multiplexing in my channel using this link. You will listen and understand more. At this point, thank you for listening. I will want you to, put your questions in the comment section. What you either don't understand or questions you want to put to me, I will answer that. And in our next lecture, I will start by answering those questions put up to me by you in the comment section. Please like, share, and subscribe to this channel so that you can be getting notifications when we are having other lectures. I'm disposed to do all the lectures for electrical and electronic engineering, computer engineering, telecoms engineering, and mechatronics engineering for all the CC maths syllabus. Thank you.